है पेन ड्राइव किसके वो मार्कर पॉइंटर पॉइंटर है कहीं पॉइंटर है श्रुति किसी पास पॉइंटर नहीं है ना दिखाना है ओके प्लीज है ओके सो थैंक यू आ गया लाइए समझ So this is going to be your last lecture, and I will not be discussing much of physics into it or derivations into it. It would be a informative lecture, but yes, you will find it good. Those who are working with the thin films. I would be talking about one of the thin film deposition technique, that is pulse laser deposition, or we call it pulse laser ablation, PLD or PLA. So here this technique can be used to grow thin films and also can be used to synthesize nanomaterials. You may have questions in between, please do ask. We'll try to answer those questions. I think until this class, there were so many, I mean, many times Professor Prem has said get thin films, GMR, TMR, so many things. So whenever somebody talks about thin films, one should ask, sir, what are the methods? How can you make thin films, right? And based on the resources, I would say, and based on the requirement or the applications, we must choose or select the technique, thin film deposition technique. Okay, so I would talk about introduction, then PLD, a detailed overview. I will take certain examples, and before we move on, one should ask this question: why do we grow thin films? Why they are of interest? What is so good or so different about thin films so that we are trying to deposit or study thin films? Anyone who can answer this question, why these films are of interest, thin films? Acha, pehla sawal, which coating is to be said as a thin film? When this word thin is said, what do you mean by thin? Less than, it's a general thing, less than 100 nanometer, if something is coated, we call it thin film, right? Why they are of interest? What makes thin films interesting? Anyone? Yes. The very first thing is properties of thin films are quite different from the bulk. When I am saying quite different, what do I mean by? Which properties I talk about? If I am interested in magnetic properties, I will look at them, right? So maybe about I would say about 20 years, about 20 years ago, we were working on one material. I think again we started working on that. That's zinc ferrite. So zinc ferrite ZnFe2O4, it was very well known in bulk as non-magnetic. If you look at zinc ferrite ZnFe2O4, I will be discussing that also. If you talk about, I think red is not seen, na? So if you talk about this ferrimagnetic material, ZnFe2O4. So here there are two sides, A and B. A is tetrahedral, B is octahedral, and in one side Zn2 plus goes, Zn, other side these two ferric ion goes, Fe3 plus, and there is one more Fe3 plus, right? When you talk about zinc ferrite, I am talking about bulk. So if you look at zinc 2 plus, it has D0ness. So it's D has all 10 electrons because 3D10, 4s2 is the configuration, right? If I say Zn2 plus, my 4s2 electrons will go out and you will have all the subshells filled, right? So all are paired. So this will give you all subshells filled. That means it has zero magnetic moment, zero Bohr magneton. Because of what? Because of all are paired, right? But if you look at Fe3 plus, it has, I think last time I said Fe is 26, so Fe3 plus will become what? 3D5. Fe26 is what? 3D6, 4s2. If you look at Fe3 plus, that means 3 electrons are out. You have how much? 5 electrons in D subshell. So there are how many unpaired electrons in Fe3 plus? 5. So there are, the magnetic moment in Fe3 plus is 5 Bohr magneton. So this will have 5 Bohr magneton with up spin. That's how they are arranged. This also have same 5 Bohr magneton but down spin. That is how they are arranged. They will cancel. So resultant magnetic moment here will be in bulk. So in bulk it is non-magnetic, I would say. It won't show any hysteresis loop. But when we deposited it for the first time, we have seen yes, it shows very good magnetization. We did that, and it was published in APL. We got very good citation to it. So the reason is what can contribute to the magnetization when you grow the same material into thin film. So there were chances that yes, my cation can interchange, ferric can go from B to A side and zinc can go from A to B side, and there is a realignment of this magnetic moment which can lead to what? Some unpaired electrons that will give you magnetic moment, resultant magnetization. So that's one thing. Okay, their properties when you deposit in terms of film, yes, you can see a quite different properties. एक और बात है, we may take some conducting material which is conducting in bulk, but when you deposit in film, it becomes insulating, right? So there are many such properties that you can see that they are changing when you grow from bulk to thin film. Why it happens? Why it happens? Why their properties are different from the bulk? First reason is films, they are of different grains. So bulk materials may have different grain size, films may have some other grain size. Second is they are not fully dense, they might be porous. Since these films are deposited over substrate, so this may result into some kind of stress. They may have totally different structure as compared to the bulk. आपने cubic bulk में है, हो सकता है orthorhombic it become in film, or tetragonal it becomes in film. So if there is a change in structure, it will result into change in properties. And then you have one more, it is strongly influenced by the surface and the interface between film and the substrate. So substrate will decide whether the film would be polycrystalline or it will be single, I would say epitaxial, or maybe amorphous. So based on how surface is contributing, your film can show different kind of property, right? And these are the few properties I have listed. These property will result these applications. For example, if you look at electron transportation, we talk about resistance or resistivity. We can see you can see the change in resistivity or increased resistivity. This is used in thin film resistors. Until last 5 days, you were discussing one of the very important parameter, that was magnetism, and it is used in magnetic memory or storage device applications. Superconductivity, Josephson device where tunneling is being studied, and then optics, you have AR coating you might be using in your specs, right? So when we talk about, I think sir is already there, I don't know, he's from chemistry or from, so but let us see. So when we grow films, these are the 3 different methods, growth methods. That's how films grow. The first method is island growth. So you have 3-dimensional islands. And in this island growth, there are interaction between these atoms. So if interaction between atom is more as compared to the atom interaction with atoms and the surface of the substrate, then the growth is island. You have layer by layer growth where the interaction of these atoms with the substrate surface is more. Then you have first layer and then the next layer. It's a mixed layer, so you have a initially layer by layer, then atoms do grow. So these are the three well-known thin film growth modes. Yes, if I talk about how to grow films, there are broadly there are two methods. One we call CVD, second is PVD. What is CVD? Chemical vapor deposition. Here basically we use reactant gases, and these reactant gases are sent into the chamber, and in that chamber chemical reaction occur, and accordingly you have a growth of films on the substrate that you place at appropriate position. You have these are the commonly known CVD methods, and it is mostly used for semiconductor industries where dielectrics and silicon is used. We also have one more method. It is physical vapor method where no chemical reaction is used. Here what is happening, you take target of the material for which you wish to deposit thin films, and this target through some means or ways, what happens, plasma or the vapors are created. These vapors or the plasma, they are of constant materials, and they expand in vacuum, make a plasma or plume we call it, and then you have a that plasma goes and sits at the substrate. You have a deposition of film, and this method is your PVD. Here no chemical reaction is involved. There are list of such methods: thermal evaporation, electron beam evaporation, sputtering, PLD, molecular beam epitaxy. Depending upon the kind of resources you have, depending upon kind of requirement you need, you may choose these either of them. Suppose if you want to deposit, if you want to make electrode of for some device, electrode means some metal you want to deposit. So this is good thing, thermal evaporation you can take copper, take aluminum, take platinum, right? Put it in a boat, apply thermal gun, right? It will evaporate the material, it will be deposited at the substrate. So you make a kind of what you call for device you make contacts. For making contacts you take you make mask. Yes, so you take mask of appropriate dimension, place it just next to the substrate. So evaporated target material will go and it will form the contacts. So that can be used for making contacts. In fact, this can also be used to deposit oxides. Those who are working with zinc oxide, very common people use thermal evaporation. Then similarly, you have electron beam. You take beam of electron and you deposit the films. Sputtering, commercially it is being used to deposit thin films for all TMR, JMR, and the other applications. Sputtering is commercially used. There are problems with the sputtering. We will discuss, not problems, but challenges, I would say. Then we also have pulse laser deposition. Again, there are some good thing about PLD and bad thing. Bad means in terms of applications and commercial viability of this system. We have molecular beam epitaxy, very expensive, but again depends what kind of studies you are trying. So fortunately, with this institute, we have thermal, we have electron beam, sputter deposition, PLD. So these 4 facilities we do have with us. I am planning to buy one CVD. Request has been sent. Hopefully, maybe in few months' time, we will have CVD with us as well. In addition to that, we also have some methods. I think these are, these are very common methods. That spin coating, electro deposition, spray paralysis. Spray paralysis बहुत simple method है. क्या करते हैं आप लोग? एक spray gun लेते हैं, vacuum create करते हैं. So the spray of liquid goes out and it sits in. Depend करता है. When you use spray paralysis, film may not be too dense. You may have huge porosity. Suppose if you are willing some film that has good, that requires some porosity, I think spray paralysis is required. So based on applications, you can choose the method. And as I said earlier, based on the resources that you have with you. So if somebody can afford to have MB, I think the best is you can have MB with you. But it's very rare, mushkil hai. Yes, these are few issues that I think you all should understand. When we deposit films, there are maybe it may be more than these challenges. These are the very important issues. Those are related to the growth of film. First is stoichiometry. If you are using multi-component target, anything that you have 2 or 3 compositions, and trying to grow films out of it, then it is quite possible that the composition is not maintained in film. So whatever composition is there in the target, same you don't see in the film. So if stoichiometry or composition is changing, then the film properties will change. So this is one of the very important thing. And it is said, let's say, as I said, sputtering is commercially available, commercially used thin film deposition technique. But if you are using multi-component target, then sputtering, it is difficult to maintain chemical stoichiometry. So those who are working, let's say, with superconducting material, HTC, YBCO, there are 4 components. And if you try to make thin films using sputtering, then it is because there 1, 2, 3, 4 is very important to maintain that. If you don't maintain that chemical composition, it will not be superconducting. So if you want to precisely control over stoichiometry, then I think sputtering will be an issue. Epitaxy, yes. If you want to grow epitaxial film, epitaxial means a film of same crystal orientation as that of the substrate. So growing films with epitaxial growth may be an issue. One has to choose method and the substrate accordingly or wisely. Impurity, yes. If you are growing films at high temperature, suppose I am trying to grow film on glass at, let's say, 400 or 450 kind of temperature. So at that temperature, it is quite possible that glass can diffuse. Glass can diffuse into film. If you are trying to grow films, let's say, on quartz substrate at 900 degrees centigrade, there is possible that quartz can diffuse into silicon, can diffuse into film. So, and there may be some other impurities that may get in, maybe because of atmosphere. So this is one issue. Strain. Depending upon how my substrate is selected, my film can have different kind of, my lattice parameter may not be same. So they are either compressed or expanded. So they may be under strain or stress, and accordingly properties may change. This is another problem, second phase. Though my target is of some chemical, structure, but you make film, then you have additional phases coming into it. So you need to overcome all of them. If you could do take care of all of them, then perhaps you can get the desired thing. And but it gives you opportunity to play the way you wish, right? Yes, based on that, I am discussing one of the method that I am discussing here. It is pulsed laser deposition. This method is very simple. As far as application is concerned, it is very simple and straightforward. But if you look at the physics, it is highly complicated, very, very complicated. So I'm not discussing because there are a lot many things to talk about. But if you look at is this method, you have a chamber. This is a vacuum chamber. In this chamber, you take targets. These are the targets of which you want to make thin films. Here I am showing 3 targets, 1, 2, 3, and 3 are in backside. So there are 6 targets mounted at here. And you see these targets are attached to some motor. So these targets gets rotated during deposition. You have just opposite to it, you have a substrate holder. There is a substrate holder. It's a holder as well as heater. So it has a heater attached to it. So you can grow films at room temperature as well as at high temperature. So here you can go easily up to 850 kind of temperature. Opposite to this substrate, there is a this is the, I would say, shutter, and then you have some ports here and there. From there you can see the plasma or what is going on inside. Here we have a port from where my laser gets in. So idea is you take high power laser, you take light, and this light is made incident to this target. Target will absorb the entire energy, and this energy will convert into plasma. Plasma will come somewhere here. If you remove the shutter, plasma will go and sit at the substrate. You will have a deposition of film. So that is how you make thin film. So you have a laser beam, and then, sorry, you get, I'm not good in making these animations, but anyway. Now the issue is there are few things which are of interest. When I'm saying lens, why do I use lens? Because the diameter of laser is little big, high, about 6 to 7 millimeter. And here it's not the laser energy that is important. To ablate the material, it's not the energy, it is energy density. Energy coming per unit area is important. So to increase energy density, you need to focus the beam, and focusing the beam, you need use this lens. और मैं जो यहाँ बात कर रहा हूँ, whatever optics we talk about, it's not an ordinary optics, है ना? इस wavelength के corresponding you need to choose lens. These lenses are specialized lenses. In fact, these windows are specialized, expensive. इसका सारा चीजें, I always keep talking in terms of cost. So the setup is expensive. So, and as I said, during deposition we keep rotating these targets. Rotation are of two type. It is back and forth. This way we rotate, and we can also rotate about its own axis. So if you want to deposit film of one target, just get hold of this target and have both the rotations here. You will be getting plasma coming out from here, and you will have a deposition of film. And if you want to deposit multi layers, again it is very straightforward. You move from this target to another one, second film will start depositing. So with PLD, it is very, very simple to deposit multi layers. Okay. Yes, that is how we see the plasma. You don't see the target here, right? So laser is being heated here. After absorbing the radiation, plasma is coming out. So this blue one is, if it is a dark room, you could have seen little better. So this is the plasma coming out, and this red one is the substrate heater. So if it is red, temperature is around 700 kind of thing. Right? So this is maintained at a temperature of about 700 right now. So this plasma is going and sitting at here, right? So when you have a plasma, there is a problem here. We will discuss those problems. This plasma, we call it plume, and this plume has lot many things to it: atom, molecules, electrons, ion clusters, bigger particles. We call them particulates. So this plasma expands hydrodynamically, and then it goes and sits at the substrate. That's the unfortunately this laser energy has gone down. I am hopeful that maybe March end I would be getting new laser, but these are the two chambers that we do have. I was telling, maybe here you can see this is the target holder, and maybe opposite is the substrate heater. Here it is the target holder, opposite to that is the substrate heater, right? And you have lot many ports. Here is this port, and down this we have vacuum chambers. It is a gate wall. We have a vacuum system. This is turbo molecular pump based PLD. This is the PLD with diffusion pump based, right? It was little less expensive. This is more expensive. So we are using both of them as per need. Although we talk about experiments, but having any experimental facility is very, very expensive these days. To get this setup, I think it will take about maybe about 1.5 crore, right? Because I'm buying one laser, this laser, I just paid about 65 lakhs for laser. Again, about 50 lakhs this chamber, and this will come. It's a very expensive business to have PLD. And this laser is a ND arc solid state laser. Maybe I'll talk about this laser also. So this is the chamber. This is a spherical chamber. Design hai, it is design. Nucera has a spherical. It is Indian, make in India kind of chamber made by Excel Instruments India. It is in Seoul. You have a cylindrical chamber, but it's okay. Both works well. And this is the substrate heater. You have a heat. This is the heater, and there is arrangement of heating this and measuring the temperature. This is the top surface of heater where we mount our substrate. For mounting substrate, we use either clamp or we use some paste, conducting paste, so that there is no temperature gradient from the surface of substrate to the substrate, surface of the substrate, right? So there is a problem here. I'll discuss this problem. If you see this right now, see this. You see this area is darker, right? And if you go away from the center, it becomes lighter. So meaning thereby my plasma is tightly focused at here, right? And if you go away from here, the plasma density goes down. So if you place your film in this region, substrate in this region, and smaller is the substrate, then the chance is that thickness of the film from one end to another will be uniform. But if you place bigger substrate like this, then what will happen? Thickness at corner will be less, thickness at the center will be very high. So maintaining thickness uniformly across the substrate is difficult in PLD. So usually we use smaller substrates, maximum of 10 mm but 10 mm size, and before we actually deposit the film, we locate the, it's a very informative lecture, I tell you. Those who are planning to work with PLD, for them it would be, or sometimes if you are planning to do PLD, for them it is good. So the thing is, you need to, before you place the substrate, first you have a blank run, blank ablation, right? And see where my plasma is focusing. So find out the position where plasma is uniform. So at that point you place your substrate, right? So if you are concerned with uniformity in thickness, then this is a very critical issue. One has to be very careful, because in magnetic materials, you basically find out magnetization. It is volume magnetization. So if thickness, there is a gradient in thickness, you won't be able to measure volume of the film correctly, and this will lead to a wrong value of magnetization. And the most important part of this setup is this laser. We are using Nd:YAG laser. If you look at the physics of Nd:YAG laser, it is basically yttrium aluminum garnet Y3Al5O12 is the structure, and it has about 1% doping of neodymium in YAG crystal. Fundamentally, it gives you 1064 nanometer. 1064 is in IR range, right? You don't see the laser light. So the most important and most critical thing about this laser is the light that is coming out from this laser is in IR range. You don't see it. Second important thing is energy is very high. So you don't see the light and energy is very high, so it is highly dangerous. If you are working with Nd:YAG laser, that too with fundamental mode, you don't see the light and energy is very, very high. High means it is ablating metal like anything. It's like bullet, gun which is firing bullet, right? So one has to be very careful, follow the safety precautions while working with the laser. And if you take, this is fundamental mode, if you go from fundamental to second harmonic, you have a 532 which is in visible range. For third harmonic, you have 355. For 4 omega, you have 266. So depending upon what kind of target you want to ablate, you have to choose these wavelengths accordingly. For oxides, we recommend that you should use lower wavelengths like 266. But the moment you look at the harmonics, second, third harmonics, intensity goes down like anything. So if you are working with 266, energy will be very, very small. If at fundamental mode it is 1 joule, here it will be about 100 joule, 100 millijoule, या 1/10 आ जाती है एकदम, या 100 to 200 I would say. But as I said, energy is not important. Energy is there, but energy per unit area is important. So, right? So if you are working with, let's say metal, maybe you may require 1064. Working with ceramics or oxides, you may use either of them. Another lasers that quite frequently used are gas lasers, excimer lasers. They don't have provision of changing wavelength. They are coming with the fixed wavelength, and they are in UV range. All are with UV range. Problem with these lasers is they are very expensive. One, much more expensive than this, more than twice. Second, operating cost is involved, because for these lasers you would be requiring these gases, and these gases are expensive. So I mean, but the thing is their laser spot is good, laser energy is stable. So there are good thing about XML lasers, and maybe if you can compromise with that, I mean, one can use Nd:YAG laser, right? These are, I said, I would be discussing some more interesting facts about it. I'm just saying these 4 things. Why do I use PLD? I have reasons to say कि सर मैंने अपनी कार क्यों खरीदी, सर बहुत अच्छी है, इसमें ये फलाना है ना. I need to tell some good thing about this. It is versatile method. Versatile means you choose any target, you can get plasma out of it, depending upon energy and wavelength that you need. It has a congruent evaporation where chemical composition can be strictly maintained. If somebody is interested with HTC kind of materials, for them it is highly recommended. Multi-component oxides, it is highly recommended because I do work with ferrites where you have more than 2 components. And majority of the researchers who are working with multi-component oxides, they recommend they use PLD. And multiple use of laser, this is interesting. Maybe laser is not part of your chamber, so this is always available. If you wish to use it for some other purpose, use it. But laser you are not using all the time, so energy is coming out, divert it to some other applications, you can use it. So that's the thing. And their reuse of target is very high. See, target is one of the very important thing. If you want to use sputtering, you need 2-inch or more bigger target, and making 2-inch target in sputtering is complicated, is difficult. You need more amount of material, and जब आप purity की बात करते हैं, purity oxides are very expensive. 99.99% pure constituent oxides are expensive, and making 2-inch target is difficult, बहुत मुश्किल होता है, टूटेगा, बहुत मुश्किल है कंट्रोल करना. And during sputtering they will crack like anything, so maintaining a crack free substrate target during sputtering is difficult. ठीक है, यदि मान लिया आपको 10 टारगेट से कुछ एक्सपेरिमेंट करना है, तो इट विल बी वेरी डिफिकल्ट फॉर यू टू, एज फार एज अफोर्डेबिलिटी इज कंसर्न, कि स्पटरिंग में आप कर पाए, महंगा है और बड़े हैं, बनाना मुश्किल. हियर you don't need such a big target. I think I can go up to 10 mm diameter target is enough, है ना. So you can use multiple targets easily, you can make these targets. So making target is easy. And I already said fabrication of multi-layer is very simple because you have multiple targets. Versatile, I will just discuss all of them one by one. We are saying versatile, why? Because the electric field, when you have light coming to target, this electric field is very high. It goes up to 10⁶ volt per centimeter because of very high power density. And this field is enough that can cause dielectric breakdown of any target, and you can easily create plasma of constituent materials, right? So here stoichiometry can be easily maintained. That's what congruent evaporation gives you. Stoichiometry I will not discuss detail, it's okay. And I said, sorry, multiple use of laser. This is the laser beam. Use beam splitters, use mirrors, and take this laser beam to different chambers and wherever you want to take them. So the good thing is, one of the most expensive part of the system is laser, and you can use it even if you are not using for PLD. And if you are to use it for PLD, yes, you can do it for multiple chambers. I think I made the setup. Here you have got 2 chambers. These are the arrangements. So from here laser beam is going up. With this mirror it is going to this chamber. If I remove this mirror, it goes to up, and from there I divert it to this. So that's how you can use beam. Please remember, whatever is being shown here, these mirrors, optics is not a ordinary optics, है ना. वेरी कॉस्टली अफेयर है, मैं इसलिए बात कर रहा हूँ बार बार, बड़ा मुश्किल है अब मेंटेन करना. There are difficulties also. Maybe I will discuss all of them one by one. Splashing of micron size particle. I have shown one thing. Maybe I'll go back. I skipped it. Yeah. No. Maybe in the next slide I'll show. So there are 4 very important, things. I would say difficulty, but we can take care of them. One is splashing of micron size particles. In plasma, you get bigger size of particles, and as a result, my surface roughness is not good. In PLD, film surface roughness is bad. You are getting very bigger, बड़े-बड़े पहाड़ मिल जाते हैं आपको. If you see the ASIM, you will see bigger particle size sitting at the surface. So if you don't need those, then this is a problem. Small area uniformity I just told, because my plasma is focused, uniformity of thickness all across the substrate is an issue. There are the challenges. Non-conformal coverage, extremely complex method, theoretically बड़ा मुश्किल है, हो क्या रहा है, हम कैसे प्लाज्मा क्या डायनेमिक्स चल रहा है, it is very difficult. Physics wise, theoretically it is difficult. बहुत कम है. Yes, people use probes, different probes. They insert probes in the plasma and then they try to study those plasma through those probes. and then they can see what physics is going on in that. So those who are working with plasma, I think they use probes बहुत सारी हैं. अब मैं उस पे temperature, growth temperature in PLD, usually films are grown or proper phase is received at observed at high temperature. So splashing, I was telling कि you see बड़े बड़े लड्डू मिलते हैं हम लोगों को ना पहाड़ मिल जाते हैं कभी कभी. So this is a problem, we call it splashing, and it is an intrinsic problem, but yes, we can get it. इससे भी छुटकारा पा सकते हैं. थोड़ा सा काम, थोड़ी मेहनत करनी है, but we can come out of it. सबसे पहला, अच्छा हो कह रहा है स्प्लैशिंग के दीज आर द रीजंस. मान लीजिए एक बार प्लाज्मा पड़ा तो यहाँ पे ये आपको ये रैंडमली ये बन जाता है, क्या बोलते हैं इसको, माइक्रोडेंड्रिट्स बन जाते हैं. इफ लेजर इज कमिंग हियर देन दिस सेक्शन विल कम आउट, राइट. सो और भी रीजंस हैं, बट दिस इज वन ऑफ द रीजन व्हाई माय स्प्लैशिंग इज गोइंग ऑन. स्प्लैशिंग को ओवरकम करने के कुछ तरीके मैं बताता हूँ. फर्स्ट थिंग इज your target has to be as dense as you can. जब target बना रहे हैं आप, try to make target as dense as you can. If the density is lower, the chances of splashing is high. So target बनाने के लिए जो pressure आप use कर रहे हैं, try to have maximum possible pressure that you can. Sintering temperature, try to have as maximum as you can so that the density can be recommended is more than 90%. So if you can maintain, observe more than 90% of density, then perhaps there is a less chance कि जो microdendrites हैं वो कम आ जाएंगे. There is one more way कि आप substrate को, you don't place the substrate just opposite to the target, rather you place it at some off axis. So directly those who are coming, those particles who are coming, particulates who are coming, they are now off. So it's a off axis deposition. और भी बात है कि बिफोर एवरी डिपोजिशन टेक द टारगेट, पॉलिश इट. सो पॉलिशिंग ऑफ टारगेट बिफोर एवरी रन इज वेरी इंपॉर्टेंट. पॉलिशिंग मतलब जो क्रैक आए हैं उसको खत्म कर दीजिए. सो पॉलिश द टारगेट बिफोर एवरी रन. एक और तरीका है कि आप यू कीप रोटेटिंग टारगेट ऑल पॉसिबल रोटेशन सो दैट एवरी टाइम यू गेट ए फ्रेश सरफेस. लेजर हर बार नई सरफेस को पकड़े, तो ऑल पॉसिबल रोटेशन यू कैन थिंक अबाउट. रोटेशन कैन बी बैक एंड फोर्थ, रोटेशन कैन बी अबाउट इट्स ऑन एक्सिस. along with you can also rotate substrate. So rotation of substrate, but technically it is difficult. Substrate के साथ connections चल रहे हैं ना, so having a rotation of substrate heater is a complicated task. कहीं है but वो बहुत ज़्यादा function करता नहीं है. There are some labs where this mechanism is there, but मुश्किल है. I could grow films. You see how uniform is the surface, and there is no, over this range there is no, I mean, those bigger particles. But there the target that I used was very, very dense, and I took care of all possible precautions, and we could grow fill with possible, though it is a difficulty, but you can take care of it. And for small area uniformity, that's how it is this. See, if you go off from the this direction, perpendicular direction, sorry, the normal direction, as the theta increases, the thickness goes down like anything. So if you want to, if you are going from here to here, thickness is going down like anything. So to take care of uniformity of the thickness, you see it is proportional to the 11th power of cosine theta. So from center to edge thickness, you are compromising with the thickness. So please be very careful. You can, yes, you can take care of that by having a rotation of substrate. Yes, you can go up to 4 inch or large, but it is expensive. Again, बहुत ज़्यादा commercially acceptable नहीं हुआ है. Yes, that's what I have said. That's how thickness may distribute. Okay, maybe I can discuss them. So there are in laser, there are few parameters, those will decide properties of film. First is the laser, and what are the parameters in laser? Energy. Energy means energy per unit area. It's a fluence, laser fluence. I think we have said fluence somewhere. Yeah, fluence, yes, laser fluence. Energy per unit area. So area you have to measure. First you have to see the spot, measure the area, and energy you can measure it through photodiode. So you got energy per unit. And the wavelength. So laser has only three things: wavelength, energy, and there is one more, repetition rate. In 1 second, how many laser pulses are coming? So rep rate is another. उसके बाद क्या बचा? Gas. If you are working with oxides, you would be using gases, right? Oxygen gas या कुछ और inert में भी काम कर रहे हैं. If you are working with oxygen deficient environment, maybe you would be using some inert gas or maybe vacuum. So the gas is third. एक तो laser हो गया, gas हो गया. Next is the temperature, substrate temperature. If you grow the film at lower temperature, perhaps you may not get the phase. If you grow it at high temperature, yes, there is a chance you can get. And the substrate, choice of substrate. One more thing is the distance between target and substrate. If you are very close to the target, yeah, growth rate will be high, but there will be problem of what? Bigger particles, uniform surface roughness will be an issue. So these are few. Yes. Okay. I all the time I emphasize on this. Laser is very dangerous. Working with laser, if somebody is working, one has to be very cautious. No outside person should be allowed when the laser is on. You should be really careful about it, because if you are exposed to this laser light, then the exposed area is gone. Sometimes it can be fatal. So if it goes direct or indirect radiation comes to your eye, you can be permanently blind. No cure. There is no absolute no cure. So one should use all possible safety guidelines listed in your lab. Otherwise, don't use it. ठीक है ना? Particularly if you are using with UV, UV don't see, and IR also you don't see. आपको पता ही नहीं चल रहा लाइट कहाँ जा रही है. So suddenly आपका मित्र है लेजर होने पर क्या चल रहा है वो पता चला, और रिफ्लेक्शन भी हो सकते हैं ना. Even reflected light can harm you. So please be very careful. हम लोग कोशिश करते हैं कि इसको बहुत ही, I may be expert in that because I had been using for many years. So I know where the laser beam can go, so I can be careful. But if somebody does not know that, then there is a chance कि laser beam इधर उधर घुस के आपके कहीं आँख में चली जाए. So take proper care. Otherwise, that's how if you change the wavelength, this is the SEM image of the target. This is the SEM image of the film. See, for the lower wavelength, roughness is good. If the wavelength is higher, roughness is high. So you need to optimize the wavelength, right? So these parameters you need to optimize. I don't say that this is good, this is bad. Based on the your application, you need to optimize wavelength, energy, TS distance, oxygen partial pressure, and whatever you can talk about. So laser fluence can also be optimized. Okay, for this wavelength, this is incongruent. Here is the congruent. So if you need incongruent, you need this fluence. If you need congruent, you need this fluence, and the wavelength region, right? So you see, if you are in higher wavelength region, splashing is more. So choice is with you. Okay. Ambience gas, target to substrate distance. There are other parameters also. हम लोग हो गया. अभी बात करूँगा. Okay, if I show you some of the yes, targets, surface roughness मैंने बताया था अभी, उसकी roughness भी important है. Density, repetition rate, these are all important parameters. One has to optimize them. I cannot say that this particular process parameter is for maybe good for your work. You need to first see what kind of films you are trying to grow, and accordingly you must choose the parameters. Here I am just showing you one effect of temperature. See, film is grown at room temperature and then gradually annealed at higher temperature. The film is polycrystalline. It is grown at quartz substrate. But if the temperature is raised, you have some diffusion coming from the substrate. So impurity is getting in, and that thing can also be there. I think ferrites, I already, Shruti has discussed. I'm not discussing this. No? This I just said. spinel ferrite, I told about it. Zinc ferrite in bulk, it has a zero magnetic moment. Now it is interesting, we synthesized same films, one was at oxygen pressure, other was at vacuum, and just by opting these two process parameters, we could observe there was a, I mean, these are the important thing. Here the lattice parameter, when you take oxygen films, it is higher. When you take vacuum films, it is lower. It is possible, it can only be possible when this iron is moving from here to here. So in zinc ferrite structure, you could see there is a cationic distribution based on how much iron has moved from here to here and zinc has moved from here to here. My lattice parameter has been changed, and this has finally resulted into enhancement of magnetization. See here, films grown at oxygen atmosphere at 850 does not show any hysteresis loop, but films grown in vacuum, it shows huge amount of magnetic field, magnetization in the film, right? And there are other associated magnetic properties that has been studied. We did it, I said, about 20 years ago since now. And this could have also been verified by looking at the conductivity that we have measured. So yes, zinc ferrite you can deposit by PLD, showing outstanding properties. Zinc ferrite, which is not magnetic in bulk, it was magnetic and it has very good magnetic moment. This was also another experiment, terbium iron garnet we use. TBIG is following garnet structure. You have three sides, A, B, and C. So iron goes to A and B side, and rare earth goes to the dodecahedral side. So these are the three tetra, octa, and dodecahedral side. That's how my magnetic moments are aligned. So resultant of this is, let's say, up. Opposite to this is your ferric magnetic moment. So why did I choose terbium iron garnet? If you look at this table, here this TBIG gives you maximum magnetostriction when you apply magnetic field along one direction. What is magnetostriction? When you apply magnetic field, it changes its dimension. So this can be used for magnetoelectric applications. So if you could see this, okay, this shows maximum magnetostriction when the field is applied along one direction. The issue is, yes, in single crystal, it has shown about 3% change in dielectric constant by changing the dimension. Now the issue is, for possible applications, you need to make TBIG having 111 within the plane. So what you need to grow TBIG with 100 orientation. So if 110 orientation, if 110 is up, then 111 will be in surface. दोनों normal हो जाते हैं ना. Minus भी ध्यान रखिएगा. So if 111 is in plane, 110 will be out. So if you could grow 110 films, you can have your easy direction of magnetization within the film plane, and then you can observe maximum magnetodielectric effect in these films. This was selected that way, and yes, we could grow these films, highly epitaxial films we have grown. You see, we choose for epitaxial growth, we had to select substrate of similar crystal structure. So we use GGG, which is gadolinium gallium garnet with same structure, and orientation we opted 220. So we could grow these films epitaxially, highly epitaxial films we have grown. There was absolutely no orientation available, and then yeah, these are the thing. And yes, when we tried to measure their magnetic thing, yeah, it was some unfortunate part at our end. We couldn't get easy axis of magnetization as we were expecting, because 111 is being easy axis. We were expecting 111 along the film plane, but we could not receive. Reason might be there is a stress coming in. We reported that, and it was again published. But when we tried to make a device out of it, we have grown GGG and then platinum, then TBIG, and again there was a lot many issues with that. Based on this spacer layer or the bottom electrode, this thickness was very important. So if the thickness was above this, there was no growth of TBIG. So we had to struggle a lot with this, but finally we could make TBIG as a bottom electrode. To study dielectric constant, you know what you need. How to get dielectric constant? Capacitor measure कर लीजिए. Bottom electrode है ना? Deep मालूम है, area मालूम है. So you measure capacitance, dielectric constant can be measured. So for measuring dielectric constant, you must have a capacitor geometry platinum is this, then you must deposit one more at the top, and then you can measure dielectric constant. It was a difficult experiment, but we did it, and yes, unfortunate part, as I said, because in our case we were expecting a 111 would be in plane, but we couldn't see that. But even then we had got some amount of change in dielectric constant. Again, this was thing. एक और हमने कोशिश किया, मैं आपको maybe I can rush it. We have grown the same film with this was very interesting. With I keep on telling to my students, with just one experiment we have published this paper in just one film, or with this result only. So why we could do this? Because we have grown TBIG with 532 orientation, right? So 532 is out, है ना? Oh, we could see easy axis of magnetization in one. देखिए ना, if you see the 532 is out, so you have 111 within the plane, है ना? 5 minus 3 minus 2 goes to 0, right? So that way we could observe easy axis of magnetization within the film plane. This was immediately accepted. Just one film, one experiment, and got. एक और issue है in thin films in PLD, growth temperature is an issue. It is grown at very high temperature. So what has been done? We placed one permanent magnet in between. This has provided some additional energy so that you could lower down the growth temperature. And for strontium ruthenium oxide, we could grow these films at STO substrate at very low temperature of 400. Otherwise, we were growing the same film at about 800 degrees centigrade. So we could reduce down the substrate temperature by 50%, and properties were almost same as that of the, see, it is almost coming same as 79 degree films. All transport properties, magnetic properties, and TC, it was coming out to be same as that of the film. Those were grown at high temperature. This PLD can also be used to make nanoparticles. What is to be done? Take the same laser beam, have a furnace, you have target, let's say आप CNT बना रहे हैं, take graphite target, then you can have a plasma coming out, and then you can collect these particles. And if you see this, it's a CNT grown by PLD. And it can also be used to grow nanoparticles. Here it is a picture. Here you take material, let's say nickel. If you want to make nanoparticles of nickel, you take nickel, have light coming to it, it is dipped in some liquid. So what will happen? The plasma will be created, and the nanoparticles will be dispersed in liquid. You can filter it out later on. Usually people use acetone, and you take the acetone on something. After some time, acetone will evaporate, and you will have nanoparticles left. But ये दिख रहा कि जितना दिखता है आसान इतना है नहीं. हम लोगों के साथ एक बड़ा, it's just an accident, I would say. The moment you shine light at here, it will catch fire. यहाँ एब्लेट होता ही नहीं है. And to prevent fire, what we did, we had some inert gas in this region, localized region, so that oxygen was not available and we could grow the nanoparticles. So you see these dumbbell shape kind of nanostructures of nickel could have been grown. So that's all. I would stop at here. Thank you so much. I am open for questions. It was a totally informative class lecture where I talked about some process of PLD and applications of PLD. If you have any question that I can answer, I would be happy to answer. 800. Strontium titanate, STO, strontium titanate. Yes, strontium titanate. Silicon can also be. Silicon. Yes, silicon can also be. Yes, no, for silicon it doesn't. Quartz, yes, I could see the damage. Strontium titanate, no. It depends. उसका देखना पड़ेगा ना. You need to check what is its melting or diffusion temperature. If you cannot use 900 or 800 for glass, if you are using glass, then it will melt. So the deposition temperature has to be very, very selective. Which substrate you are using. Let's say if substrate is getting melt at that temperature, then you won't get anything. Rather, the system will go waste. Yes. Okay, for controlling thickness, it's a good question. See, what causes thickness? The plasma. So what you have to do, first you have to calibrate. Either we have thickness monitor attached to the system. If not, what you do is you optimize the conditions, put it somewhere, write it somewhere, have 3, 4 or 5 depositions, and measure thickness outside. Take the film outside and measure. And when you are doing deposition, you do it at different time. Let's say 5 minutes, 10 minutes, 30 minutes, and so. So you have got 5 data points, and then you calibrate with this much time, this much thickness you are getting. So then you can have a control over time. The only thing is, in that case, rest of the parameter should remain same. If you are changing any of the parameter, immediately the thickness will change. If oxygen pressure changes little bit, your thickness will change like anything, because plume changes like anything. It is highly effective on oxygen pressure, highly dependent on oxygen pressure. So one has to be very careful at oxygen partial pressure. If it is maintained at, let's say, 1.6 millibar, then maintain it at 1.6 millibar. So maintaining at that pressure is a task. So anything else? And then once you have calibrated, then it's okay. For one target with one fluence, what temperature you have calibrated it, now you can deposit the film as per your thickness. There might be some variation thickness. Even if you calibrate, you will find yes, thickness is not all the time coming same. Thoda bahut margin aata hai. But you can have some idea that this is the thickness of the film, typical thickness. Yes. I told you interface, substrate, surface roughness, film की surface की, substrate की, film की. Very first thing I said कि आपकी जो energy fluence है, that should not be very high. Try to have energy fluence just above the threshold. Suppose threshold is 2 joule per centimeter square. Threshold समझते हो? Minimum value of energy density that is capable of ablating the plasma, है ना, making the plasma. Let's say it is 2 joule per centimeter square. तो आप इसे थोड़ा सा ऊपर रखिए. Don't make it very high. So energy fluence should be just above the threshold. One thing. If it is very high, then it will carry bigger particles to it. दूसरा, the target that I told earlier also, that the target that you use, it should be of highest possible density, है ना. तो जब आप बना रहे हैं तो उसको जब पैक करते हैं आप थ्रू प्रेसिंग मशीन, व्हेन यू प्रेस, यूज मैक्सिमम पॉसिबल प्रेशर. वो भी देख लीजिए, कहीं पता है वो टूट जाए, ब्लास्ट कर जाए वो. सो पीपल यूज साइक्लोस्टैटिक प्रेस, CIP बोलते हैं, दैट कैन प्रोवाइड very high pressure. Otherwise जो हाइड्रोलिक होते हैं उतना प्रेशर नहीं दे पाते हैं. So if you are using CIP, then you can get very good pressure. Third, you must center that target at high temperature, maximum possible, so that उसकी compact density बहुत ज़्यादा हो जाए. Next is, before every deposition आप उसको polish कीजिए. You take fine polishing paper and polish it, make it very shiny, जैसे टाइल्स ऐसा बना लीजिए. तो जो rough surface होगी उसकी वजह से splashing कम हो जाएगी. So these are few things that you have to take care while. If you manage all this, then the surface roughness can be taken care of. Exactly, yes. Yes, these are the, you need to optimize, play with all these parameters. There are a lot parameters to play with. But good thing, as I said, good thing is कि आप chemical composition maintain करते हैं. तो आपको device बनाना है बहुत छोटा सा, तो that is good, है ना. तो the only thing is कि अभी मैं बात कर रहा था, जैसे मान लीजिए मुझे किसी प्रॉपर्टी बेस्ड कोई हम यदि डिवाइस बना रहे हैं, और इफ दैट प्रॉपर्टी इज लॉस्ट एट हाई टेम्परेचर, देन वन हैज टू बी वेरी केयरफुल. सो ग्रोथ टेम्परेचर इज एन इशू. यस. एनी अदर क्वेश्चन दैट यू हैव विद यू? क्या? हाँ हाँ मिलती है सर. हम तो 4 कंपोनेंट हमने मैच किया है सर, कोई कहीं इशू नहीं है. आप हमने एडेक्स देखा है, बिल्कुल एटॉमिक परसेंट तक मैच करता है, कोई इशू नहीं है. PLD आई हैव सीन, इट इज एब्सोल्युटली ओके. रिपोर्टेड है सर, हर बार रिपोर्टेड है. यस. स्पटरिंग में तो यू विल ऑलवेज, यू हैव टू कॉम्प्रोमाइज विद दैट. यस, इट इज नॉट रिकमेंडेड. स्पटरिंग इज नॉट रिकमेंडेड इफ यू यूज मल्टी कंपोनेंट. हाँ, फिर आप क्या करते हैं, पहले एक मल्टी, वो आपके पास अलग अलग टारगेट यूज करते हैं. फिर आप मल्टी लेयर काइंड ऑफ थिंग्स यू आर गोइंग, अदरवाइज एक टारगेट का बनाते हैं थोड़ा मुश्किल है. YBCO, I think it's never reported using sputtering, if I am remembering correctly, because there 1, 2, 3, 4 is very important. If that ratio is disturbed, then it will not be superconducting. So there it is important. Yes. Yes. Any other question? So if not, is that okay? So I will thank you all for being with me in this informative class of